Hello, today I'll be explaining to you our code for AES encryption via energy harvesting. So, to begin, in our init function, we are going to stop our watchdog timer, set our board clock to be 1 megahertz, and then set a clock divider to be a third of that for flash timing. After this, we are going to enable our ADC by enabling interrupts, setting some registers, waiting for a delay, and then setting our ADC input. Now, later on, I'll describe to you why we decided not to use the ADC, even though originally this was our plan for detecting our input voltage and the changes associated with an energy harvesting setup. After this, we set a button, and that's the onboard button on pin 1.3. We initialize our AES. We set our LEDs that are on board, and then we get a counter from flash. Now, this counter right now at the beginning of our iterations is set to 0. However, as our AES ticks through each iteration, we are going to increase this counter, and after a certain point, we will stop doing encryption on our block of data. Now, to begin, in the main loop, we have a endless loop, and inside of that we have another while loop that while we are below our max iterations, we are going to set our pin to be green and then start the encryption, AES encryption on our block of data, and then stop the LED once it is done with the test encryption, and then iterate our counter. And if our counter is equal to the max amount of iterations, which in our case is 100, we are going to break out of this while loop. In addition, in the while loop, we are sampling our ADC and then setting some status bits in our register, which will then be turned off once our interrupt from the ADC triggers. Now, if the value in our ADC memory is greater than this 3FFF, which in our case is greater than or having our board be less than 1.5 volts input, we are going to set our LED to be blue, save our counter, and then turn off the LED once our counter is saved. Now, if all of this is done and we are broken out of our while loop, we are going to be, again, in an endless loop of checking our button state and setting our LED to red. Now, if the button on board is pushed, we are going to set our counter to 0 and begin iteration again. Moving down to our interrupt service routines for our ADC and our timer, we see here that our ADC interrupt is going to clear this CPU bit, which is a low power mode, from our status register. And on a timer, it's actually going to turn on this bit, and that you'll see that in the timer 0A0 vector. Now let's look at the board in action. As you can see, the LED cycles between green, blue, and red, and green being the calculation for AES is taking place, blue being the state is being saved, and finally red when the amount of iterations is done and it is currently waiting to either be reset or to continue on in the while loop. Now, as you can see, when we press the button, it effectively sets our iteration counter to be 0, which in that case also sets the flash memory to be 0. And now we're going to look at the oscilloscope trace. The blue line here represents the input voltage from our PowerCast setup, and you can see that it cycles quite a bit, and that's just representative of the capacitor on the PowerCast setup charging and then decharging. The red line represents our LED, which is only turned on when we are done with our encryption. As you can see from our math here, 100 encryptions takes about 50 cycles, which is about 14.5 seconds. Now, we were asked to do 8,192 encryptions, so that would be about 4,096 cycles, which would take about around 20 minutes. Now, we decided that because of how quickly the encryption gets done and how efficient the encryption gets done, there wouldn't be much difference in the amount of time it would take for each encryption cycle. So we just decided to use 100 encryptions and do a little bit of quick math to figure out how long it would take for 8,192 encryptions. Now, I mentioned before that the ADC would not be a good method to test input voltage to test for a power drop. And that is because, as you'll see here in the equation I have on the screen, that the input voltage along with the reference voltages affect how the ADC samples. Our original idea was to use a voltage divider that took the input voltage and outputted a voltage that our ADC would sample and then save state when the ADC sample was below a certain threshold. But again, because of the relation with the input voltage to how the ADC samples, we could not use this method. Instead, because of how efficient our AES algorithm was, we deemed it to be okay to use our current method of saving state every encryption cycle. And through this, we can still see that our state is saved and the encryption does get completed, and that we can restore state after a powered down condition.